All right.
All right, we are recording, sir.
Cool. 3, 2, 1. All right. Welcome, everybody, to a new year. It's been a couple months since Lee and I have done a podcast, but we're back and better than ever. We're jumping into the quantum realm today, as you can tell with the title, Quantum Computing, which we've hinted at in previous episodes, but now we decided to finally dive into. So before we get started, let's just do, kind of a brief review here. Let's just go all the way back to the beginning here with physics. Now, Lee, I know we've mentioned this before, but what is it about physics that fascinates you so much?
Yeah, I think it's the fact that physics is really the observational part of physics is you're observing a phenomenon, and then you theorize some mechanism which causes that phenomenon, and then so that's sort of the theoretical physics side of it. And then the experimental physics side of it says, okay, now let's test that theory and see if it really holds up all the time. Because I could say, every time I walk out my door, my neighbor floods her backyard. And it's like, okay, why don't we do a few experiments and see if that's actually true? So that's really, I think, what attracted me to it is I can look and say, why does that fan look like it always spins off axis as it goes faster? There's some physics behind something like that. And that's, understanding the world around me, I think, is what drove me to it.
Yeah, the fundamental why question, right? That's, yeah, what you mentioned about theoretical and experimental reminds me of what I think like Einstein and Tesla say about intuition, where you have this inkling that something's not right or something's interesting, and you're like, well, why is that? And then, physics and other fields, of course, their job is to peel back the curtain behind that. And that's what we'll continue doing with these videos. Now, again, the last video we did was a fun live question and answer about time travel. Thanks again to all who watched and interacted there. It's it's an endlessly entertaining topic with questions that just hurt your brain, right? My brain just shuts down at some point. I'm like, I have no idea. I have no idea what's happening with time travel. But additionally, if you're watching this, don't forget, like and subscribe to whatever channel you're watching this on.
Smash that like button, right? Got to smash it hard.
Yeah, I mean, you could just press gently if you want. If you do have aggression to let out, smash it. Get it out on the like button, not on somebody else. But yeah, or again, always leave a comment if you have any questions or any other topics. We'd love to touch on anything else as well. All right, on to the fun stuff here. So, quantum computing. Quantum, Lee and I were discussing this beforehand a bit, but quantum seems to be all the rage these days. People using it for all sorts of different terms. But Lee, maybe if you want to give us a quick sort of rundown maybe of quantum itself and then why we're choosing quantum computing here.
Yeah, so the term quantum really came out, it really was designed, really came out about in the early 20th century as we went from physics really being classical physics. That was like Newtonian physics and thinking about things macroscopic that we could observe, and moving into the realm at which we couldn't easily observe them with our eye. And that's one of the first things that really triggered that was in the very late 19th century. J.J. Thomson discovered the electron, and so we started to have an understanding that, like, oh, so these, this piece of paper here is made up of smaller particles, and those particles are made up of smaller particles, and those particles might be made up of smaller particles. And so really trying to understand what is the fundamental building block of nature. And that really is what the idea of quantum is.
Now, let me make sure I have this right. Basic physics, there's protons, neutrons, and electrons, right? Well, for an atom, I guess.
For an atom, right.
Okay,
That's what we understand. In general, in physics, you sort of separate things into leptons and hadrons. But yes, an electron is actually a fundamental building block. But as they studied protons and neutrons more closely, they actually discovered that they're actually made of quarks.
Right.
And quarks are actually fundamental building blocks.
Right. Because I asked, when you said the discovery of the electron, I wonder, because from what I understand, protons and neutrons don't necessarily move, but electrons do, right? They have movement. So was movement of the electron something to do with the quantum realm?
Yeah, absolutely. So, by and large, you can think of the nucleus of an atom is pretty stable. It's not going anywhere. They're very heavy particles. Protons and neutrons are about 2,000 times heavier than electrons, right? So they're like sort of this fat old man sitting on the couch. They're not going to move. And electrons are like a sugar rushed 4-year-old just flying around. And so they are orbiting the nuclei really quickly. And so we started to, they started to observe that, hey, actually, sometimes these little electrons, sometimes they'll leave the atom, right? Sometimes they come off. And so that was really the first observation that, like, oh, you have this central element, and then these little tiny particles around it actually can be peeled off fairly easily.
Interesting. Yeah, your analogy is good. I think also of I got a puppy a couple months ago. He's 6 months old now, and I think of him anytime he gets hyper. I guess zoomies is the term for it these days, and it's really strange actually. He literally does circles around me, but then it spirals closer and closer until he ends up right at my feet. It's like a physical or a physics spiral. It's very bizarre. But
gravity, two bodies. Maybe you're the sort of sun, center of his universe, and he's sort of
he's like, no way I'm going to go directly there, but I will get there eventually by going in circular motions. So yeah, it's very similar. It's funny. Okay, so we've got electrons and we've got the beginning of the quantum craze. How do we end up getting to computers from there in 30 seconds? No, I'm just kidding.
Yeah, interesting. So well, and so I'm thinking about like quantum computers. What we're going to talk about today is as we found out that electrons were these fundamental pieces of an atom, then we realized that you can discretize where an electron sits in an atom.
What does discretize mean? Sorry.
So discrete levels.
Okay.
So that, like, imagine, when you're in a blank room, you can, by and large, kind of position yourself anywhere you want in that room, right? You can move an inch to the left, an inch to the right. If you go into a movie theater to sit down, you can either sit down only in one seat, so that you have very discrete positions.
Okay.
And that's the way an electron goes. It's like, to go from one level to the next, it can't go halfway. It's either in level 1 or it's in level 2.
Okay.
Was sort of the first discovery that, like, oh, so they have these discrete quanta of energy that allow an electron to travel in these states. And so then we started to discover, okay, well, how do they organize themselves in these states? And can we force them to be in various states? And if we can force them to be in a state, then we can record them and say, okay, so you're in state 1 and you're in state 2. Okay, great. So it's either in state 1 or state 2. So this was sort of the birth of a classical computer, in that you could say it's either on or off, right? That's very easy for us to understand. Imagine you have 2 electrons and you are, 2 electrons, and you say, okay, well, this one can be up or down, and this one can be up or down. So therefore, through the combination of those 2, I can actually get 4 combinations. I have 2 particles with 2 states. 2 squared is 4 different states. If I add a 3rd electron, 2 cubed is 8. And so this essentially was the building block of starting to form a classical computer. What we're going to get into today is, now they're saying, well, there's actually a quantum phenomena called superposition, where it doesn't have to be up or down. It could be both. So you have 3 states, which seems like maybe a trivial change. But if you think about it, we said that if you had 3 of these, 2 cubed is 8, but if you had 3 states, 3 cubed is 27, and so on. It scales significantly higher. So if you could make quantum computers with the same efficiency and the same structure as a classical computer, I mean, the gains you get from that are massive. I mean, you're talking hundreds, thousands, tens of thousands, depending on your application.
Sure, sure. Yeah, so again, so with binary, it's either on or off, 0 or 1, but now the third option is it's both on and off.
Yeah. And that's
Interesting.
what we're going to get into today.
Yeah. Real quick, backing up a moment with the discrete levels of moving from one level to another or state to another. This is a bit technical, but do you know, are there infinite amount of different states, or is there a certain amount of different states that an electron can go back and forth to? Because they can't go halfway between.
Yeah. So yes, if you talk about an electron in a hydrogen atom is only going to ever have one electron. It's got one proton, and therefore it only have one electron. You try to put 2 electrons in there, it's going to say, no, it's too much. One, maximum occupancy 1. Mm-hmm. And so there's only a set number of levels that you could, finite levels that you could put that electron in. If you keep adding more and more energy, at some point you get to what's called the ionization threshold, where then the electron says, honestly, I've got too much energy for this. I actually am not going to stay around this proton anymore.
This party's too boring.
This party's way too boring. I got way too much, so you give somebody enough money and it's like all of a sudden they don't hang out with their I don't know, maybe it's not a good analogy, but if you think about something like uranium, which has many different protons, 200 or 100 and something protons. I can't remember exactly what uranium is, but if you think about all the levels it could be in, electron levels have many different states. They have something called spin. They can be spin up or spin down, which is kind of one of the things we were talking about earlier. And if you think about level 1, it could be spin up or spin down in there. Level 2, there's 3 different positions. Each of them could be spin up or spin down. Second one is 10, spin up or spin down. And then there's many different quantum levels. So they're not infinite, but you get to the point where the number of combinations you could put an electron in is probably in the thousands.
Okay.
So more than that, depending on the number of variables that you're doing, probably tens of thousands or maybe millions if you talk about combinations with other electrons.
Yeah, that's fascinating though, that they're still bound by some kind of state. Like they can't just go halfway. They have to be all in, or all out. Cool. All right. Back to the plan at hand here. So getting a bit more in detail here, you left off with the uncertainty principle and superposition. Let's dive a bit more deeply into that. Again, maybe a brief review. How does that relate in more detail to the quantum computing or to the quantum realm? And why is it so important? I know you went over the 3 cubed versus 2 cubed, but
yeah. So in thinking about the uncertainty principle, the uncertainty principle really was really formulated by the EPR. Heisenberg did the initial work on the uncertainty principle, and then Einstein, Podolsky, and Rosen, I think, did further work on it, and they also actually came up with the concept of wormholes. But basically, what the uncertainty principle states is that if you want to look at an electron or a fundamental particle, you cannot know its position and its momentum to an infinite degree of accuracy. If you know the position really well, you're not going to know how fast it's going. If you know exactly how fast it's going, you're not going to know exactly where it's at. And this is just all comes out of the fundamental nature of our universe and is theorized and presented in quantum mechanics. There's different interpretations of this. You could also think of energy and time. So you could know exactly what an electron's energy is, but you don't know exactly when you detected it. There's some error bar associated with that. Conversely, if you say, hey, I know this came in at exactly this time, you're going to have some spread in its energy. The technical, the technicality you have to do when you're going into calculations of uncertainty principle involve things like doing Fourier transform and eigenstates. So it gets very technical, but when you zoom out, it's kind of interesting that you can't know them both with 100% accuracy. And something that comes out of this is it actually turns into a joke in physics. It's called quantum fluctuations. And so the common joke in physics is if you get something wrong, you just say, oh, it must be due to quantum fluctuations. It's a joke, but it actually corresponds to the uncertainty principle. And in the uncertainty principle, quantum fluctuations have to do with the fabric of our universe having some uncertainty. And a good example of that is something called virtual particles. So what you can get is you can have a perfect vacuum, nothing in it. Let's say that you want to have just pure vacuum, right? You're a purist, and you're like, kind of like people want like a pure iceberg water or something. I want a pure vacuum, right? You create it, you get all the electrons in there, you find one, you're like, oh, get that guy out of there. Okay, completely empty. Out of vacuum, you can get particles that come out of nowhere. And what they will do is, because of the uncertainty principle, they can appear out of nowhere. Like you can get an electron positron that can appear out of nowhere, and then they will annihilate each other and sort of like come in and out of the fabric of the cosmos. And that is, one of the things that happens as a quantum fluctuation is that there is some finite, maybe small probability that will happen. And so this is how you get, sometimes electrons can get bumped into an excited state without having any energy dumped in. There's a quantum fluctuation that bumped them into another state. And again, this is just the nature of the universe, that we live in a world that is fundamentally uncertain at the microscopic level.
Sure. So this might be an unanswerable question, but so is that the consensus more that there's an uncertainty at some level of the universe that you just won't be able to explain, or is it just that it's a force that we haven't been able to discover yet or fully explain yet, if that makes sense?
It seems to be that it is just it just has to do with the nature of the world that we live in. It is due to this uncertainty principle. And while there may be some discovery later on, this doesn't seem to be one of those things. Like dark matter and dark energy are sort of terms for something we truly don't understand, and we just need a label for it. Quantum fluctuations and the uncertainty principle come out of theoretical physics and are proven in experimental physics. And we just understand that the nature of the world we live in has some uncertainty. Again, when we scale that up to the macroscopic level, I know that if you are sitting there right now, in a half a millisecond, you're still going to be sitting there. There's not a finite probability that you are all of a sudden going to disappear.
I didn't.
But it seems, it seems weird when you try to apply our macroscopic understanding of the world to the microscopic world.
Well, because I think like right now in normal time, it would be very strange. Like you just don't ever assume that I would just disappear in the next millisecond. But if we slowed time down to, a millionth of a millisecond, and we're living that out, right? It then becomes much more probable that maybe he does disappear, 1,000 years from now when we finally get to that full millisecond, when we finally experienced it in that case.
Yeah, I mean, there's there's a concept called quantum tunneling, which again, when you think about quantum tunneling is essentially that if a particle comes up against a wall it can't go through, there is a probability, a finite probability that it will make it through the wall anyway, right?
Crazy.
There's not, like as many times as you and I run into a wall, there's not a probability that we're going to go through it. Now, this has to do with the number of particles and the number of the number of states in our wave function. Given an infinite amount of time and tries, there is a probability that we would teleport through a wall. Again, like when you think about what it takes, a single particle teleporting through a very simple barrier is a lot. It's a finite probability that it will tunnel through that and do what's called quantum tunneling.
Reminds me of that quote from Dumb and Dumber where he says, "So you're saying there's a chance," after she's like completely and utterly rejected him, but he's like, "Well, but there's still a chance."
Yeah, what is it like? One in a 100? And she's like, more like 1 in a million. And he's just like, he puts his head down. He's like, so you're saying there's a chance? Yeah, you're right. That's a good one.
Oh man, yeah, that is fascinating. Okay, so we might have already touched upon this a bit, but it does, I think, help to bear out a bit more of it. It is weird still to think about like not being certain of where something is. How do physicists reconcile that beyond, the classic quantum fluctuation joke?
Yeah, I think physicists are probably better than anyone at like the cognitive dissonance of like understanding how something works on one level and then not letting it affect other levels, right? Like you wouldn't change your driving patterns assuming that like maybe somebody could be in a superposition of two cars, or maybe we're not going to know their position, right? The car is going to move over. But I think that's really what we struggle with when we start thinking about these concepts is we use the reality we live in as an analogy and try to come up with an analogy of that. And then when the analogy doesn't make sense, then it really is, it's just, in our minds, a theoretical concept. Unless you are a physicist, we don't usually concern ourselves with that. So I think that is the difficulty, is like the reality in the macroscopic world we live in has a very specific application of physics, mostly classical physics, right? We see gravity working and we see we see light propagate to us, but we don't, think about some of the nuances of it. That is that we don't see all the light because some of the light, might get changed its trajectory by a quantum fluctuation or something. By the time it gets to us, we're going to see 100 million light rays in a beam of light instead of 100 million in one.
Yeah. I mean, it's similar, obviously, to like, a human versus a dog, right? So whenever I take my dog out for a walk, he just finds random things immediately by smelling, or he smells something, and I have nowhere near that amount of sense. And I'm okay with it. I don't really want to smell everything all the time, but he seems to love it. Same with physicists, I guess. They're fine with compartmentalizing these types of things without going insane, hopefully.
Yeah.
Because it is, I mean, if you treated that as a religion, you probably don't end up too well off, I'd say.
I think, in my experience in physics for a couple decades, I think you generally find, you will find the type of person that, they live their research, and they actually are not going to be concerned with the outside world. In some ways, that's a distraction because their mind is always in this sort of, analytical state. And, they spend a lot of time on sort of like metacognitive state where they're thinking about putting themselves in these thought experiments. And it's weird to us. I mean, I had met people in grad school that had never been out to a club, had never played a card game, never been on a date, just like the things that we think are a natural part of like growing up, they never experienced. And I think a lot of that is the type of work that you're doing and the headspace you try to be in.
Yeah, I mean, that gets back. I was thinking earlier when you're talking about the quantum fluctuation, but from what I understand, Einstein, after he'd gone through with his major accomplishments, he still was driven by this quest for like a unifying theory of everything, right? And it kind of, I mean, that's what everybody wanted for a long time. And then I guess with this quantum fluctuation, that would help explain why that's not really ever going to be possible. But it did consume him, from what I gather, in a way.
Yeah, specifically, Einstein was concerned with general relativity and quantum mechanics, right? He had come up with these beautiful theories of general relativity, which describe gravity, and then quantum mechanics. I think, Einstein had this knee-jerk reaction that when quantum mechanics came out, I think in his head he was like, well, it doesn't coalesce with my theories, so there must be something wrong. And then the more he studied it, the more publications, he realized, okay, this is no fluke. Quantum mechanics is real and general relativity is real. So how can they both be real, but they don't agree at the microscopic level, right? At the macroscopic level, they agree just fine. At the microscopic level, there's major problems and inconsistencies. And he wanted a way to reconcile that. And this is the idea of the theory of everything, basically.
Right. Cool. All right. So back to, the uncertainty principle a bit more. So this leads a bit into philosophy too. These things kind of all coalesce in the end. But give us a quick breakdown here of Schrodinger and Schrodinger's cat, and how does that relate to the quantum realm and uncertainty principle?
This poor cat, man. I guess luckily for you, it wasn't a dog, but so Schrodinger was one of the founding fathers of quantum mechanics, and he actually designed a thought experiment in cooperation with Einstein. Einstein was famous, probably one of the best thought experimenters of our time. And he designed a thought experiment to try to reconcile this concept of superposition and bring it into the macroscopic world. And he did an excellent job of that. So he wanted to bring the question of, when does an actual quantum state become a non-trivial linear combination of states, right, that affect the macroscopic world? And so he did this by saying, imagine you have a cat in a box or a cat carrier or something. And what you have attached to this cat carrier is you have a radioactive substance in another, let's say it's in an isolated room. It's not going to hurt the cat or anything. The cat doesn't even know that it's there. You have this radioactive substance in a container, and you have a Geiger counter waiting to detect radioactive decay. So people are probably familiar with the term half-life. For one, it was a really awesome video game, still is. I think they're in development of another version, but also because half-life dictates how long a substance stays in a state before it decays what is usually an extreme particle, sometimes an X-ray, sometimes other dangerous particles, but it decays that particle. And there's only a probability that it will decay. The idea of a half-life is that if you have a substance, let's say it's got a half-life of an hour, statistically speaking, if it's got a half-life of an hour, after an hour, half of it is going to be gone statistically within some margin of error. So what this thought experiment says is, okay, imagine you have just one of those particles and you wait an hour. There's a 50-50 chance that it will have decayed. If it decays, you have a Geiger counter to measure that. The Geiger counter is connected to a vial of acid, which it dumps in the cat's carrier, and the cat dies. I don't know, these experiments, something's always got to die.
Sorry,
so
Peter.
So the cat would die. And so what this basically puts together is that now the cat, within that, as you observe that cat within the hour, the cat is actually in a superposition of being alive and being dead, right? Like, let's say you leave the room and you wait an hour. You don't know whether that cat is alive or dead, right? There is a finite probability that it would be 50% probability that it'd be dead and 50% probability that it'd be alive. So actually what you've done is you've taken a superposition of a state, a quantum state, and now you've tied it to a macroscopic state. And so now the cat is in a superposition of being alive or being dead. But that again brings to light what we talked about, that that really doesn't jive with our understanding of the universe, right? You are either alive and you're alive until you're dead, basically. You're not in this sort of superposition. And so that's basically what the thought experiment is meant to do. It's meant to bring forth this apparent paradox. And so I'll swing it back to you. How would you think about it? Does it seem weird to you?
Yeah, I mean, it seems somewhat weird, but I assume, going back to what I did with the milliseconds, expanding that out. I mean, if you think about a life, I'd say, Lee, at age, how likely it is that you're going to be alive at age 100? I don't know what it would be. Maybe, maybe 5-10%. Who knows? Maybe higher, depending on medicine. And if I increase that up, it's going to go down and down and down. 130.001%. But at some point, you're dead, right? It's it's like, well, I don't know if Lee's going to be alive. He's either alive or dead when he turns 100, right? If you think about the future. Now, in the present, if you transfer that same principle to the present moment with the cat, yeah, I mean, the assumptions that we carry around with us in everyday life, like I assume all of my family is alive right now because I heard from them recently, right? So it's an assumption, like, but technically, I guess it is possible that they're either alive or dead, right? Because it's possible. I don't want to even put that out there, but just as a thought experiment, like, I don't know for sure. I'm assuming based on high probability because I just spoke to them that they're alive, right?
Yeah, the alive and dead thing always makes it a weird thing to talk about. It's like, why does the thought experiment have to result in a cat dying? But yeah, so there's different interpretations of this from a physics standpoint. And I think in some ways, physicists battle with this more than maybe the layman, because, a superposition of states is bound by that superposition, and it is both of them. It is physically proven to be in both of those states, and it doesn't come out of that state until it's observed, right? We talked a little bit about this in podcast 2, that it's just going to remain in this superposition until it is observed. And this is what's commonly held as the Copenhagen interpretation. And that is that a system stops being a superposition of states once an observation takes place, right?
And that gets back to what you mentioned at the beginning about how you can't measure the two different qualities about a particle. It needs to either be one or the other, right?
Yeah. And I think, it's even the Copenhagen interpretation, you'd wonder, is the cat a sufficient observer, right? Like, because the cat is observing, is the cat observing whether or not it's alive or dead, right? Like, it's alive until it's dead, right? It doesn't observe that it's dead, it's just dead. So does it take someone else to observe that for it to stop being in that superposition? And that's, again, what goes into superposition. And we've proven that with this really crazy experiment we talked about in podcast 2, which was this delayed choice quantum eraser, where honestly, you don't know what screen the electron hit on. It hits on both of them, and unless you force it, unless you observe it, then it only hits in one. And so again, this is the idea of this paradox.
Yeah, I mean, that seems to, for me at least, to closely correlate with sort of philosophy and like the opinion on whether there's objective truth or not, right? Is there truth outside of the human experience or perspective? Like, so is there something that exists outside of my own beliefs or outside of my own observations? So I guess physics then would say about a particle that all of the things that could exist until you observe it. Is that correct?
Yes. And that's basically, that's essentially the Copenhagen interpretation. There is another interpretation, which I think we touched on this last time. I mean, there's a few. Another one of them is a many worlds interpretation. And that is that up until the point, like when the cat is in that superposition, there's actually, there's just one timeline. And then when we observe the cat we observe the cat to be alive, there is actually a simultaneous world, another parallel universe where the cat is alive, and that is a branch in our simultaneous realities of those two. And this just happens continuously, right? People talk about the butterfly effect, taking this to a macroscopic world. There's fascinating stories on Reddit where people talk about, God, if I had left the house today, I would have died, right? Mm-hmm. Like I left the house, and as I would normally back out of my driveway, this massive tree fell, and I would have been crushed and died. So is only because I remembered that I left the tea kettle on, and I always forget it. And so, we probably always live in this constant world of like making a decision A or B. And so, there's probably an infinite, quasi-infinite number of universes, because if it's based on every tiny little particle change, then for the entirety of the universe, then there's too many to list.
Yeah, I mean, that's always fascinating. This is slightly off topic, but I remember there was one time I was driving. I was younger, so I was driving a little fast. Of course, I'm definitely a responsible citizen now, never drive fast. But it was raining, and I was on a 2-lane street. It was probably like 35 miles an hour. I was going a little faster, and I changed lanes. The problem was, at the same time, another car in front of me changed lanes and then immediately wanted to turn left. So there was a car immediately in front of me stopping, and I had to slam on my brakes in the rain. And as I was slamming on my brakes, I swear this is true, I envisioned me getting in the car accident, talking with the person, getting my insurance, getting my car totaled, having to buy a new car. I experienced all of that in that one split second of a moment. And then once that passed, the car luckily turned, and I didn't get in an accident. It was a very bizarre moment, but I know you could always just say it was like a hallucination, but I definitely experienced it. It was very strange. I experienced all of that time. Maybe it was another universe, an alternate timeline where it didn't actually happen because I got saved by that person turning.
Well, if we want to talk, I always think about like, what physics can we make to understand this? So, is it possible that particles can entangle in simultaneous timelines, and when those timelines branch, are those particles still entangled, or is it two sets of entangled pairs? And is it possible now that when these particles entangle, you can entangle information, right? So is it possible that like the other universe entangled information, and somehow when some of those particles hit one of your neurons, the decoherence basically triggered the memory or the reality of the other one, right? Like the easy thing for us to do, and what a psychiatrist would likely do, is to say, yeah, you must have had a little episode there, or you had a hallucination. Right. But do enough people have hallucinations, right? Like UFOs and all these things. It's a good example of like, do we have to apply some finite probability that that's the case?
Yeah, or even like people seeing their whole life flash before their eyes, right? Like that shouldn't be possible if it happens in a split second. But somehow you experience it. Yeah, I like the entanglement thing, because it's almost like those particles or those neurons kind of decompressed and then let me experience it. I don't know. It's an interesting theory. I like that one.
Yeah, and you could say that like the probability of that happening is so low that maybe it only happens once in a lifetime. Maybe you're the one person it happened to in a lifetime, and you know why that works out well? Because nobody's going to believe you, right? Everyone is going to say that you hallucinated. If it happens to two people, right, they're going to say that, right? It's not unless that probability becomes high enough and happens to enough people that like we could recognize that, oh, maybe there's something we don't understand. And that's the differentiating factor of like what physics is usually explored and what is sort of written off as like, that's so far-fetched, like we just don't have a reason to
Yeah.
to think about that right now, or to put resources towards it.
Right. Although I think the greatest tragedy would be to merely write it off as an hallucination or something like that, right? You at least got to leave open the possibility that there's something weird. Like I think like deja vu is probably something similar to that. It's some kind of entanglement, perhaps. It's fascinating because I don't know if you ever had that feeling, but it's definitely like I don't ever have another feeling like deja vu. Like it's named for a reason. Like it's something very strange, and you don't really know what it is. You could just say, oh, it's just you felt the same thing yesterday. I guess so, but you know.
I thought I had told you about this story. I had a time in graduate school where I thought about like what could possibly explain deja vu and what could explain, twins who say they have the same thought at the same time or like somebody's like, oh, I was just about to say that. Like, is it possible that information contained in your brain in neurons, is it possible that there's some wave function associated with that can get entangled with a neutrino or other particle that's always going through your head? And then is it possible for it to entangle that neutrino and that neutrino to decohere that wave packet in someone else's brain? And my professor was like, well, he was like, it's an interesting theory. He was like, I can't think of a way to immediately disprove it. And I was like, yes, it's true.
I'll take it.
Yeah. So I think that's, again, it's interesting to think about like the possibilities for things like that. But me being a physicist and being keenly aware of the statistics, is it just more likely that's something in our brain that we don't understand? Yes, probably.
Quantum fluctuation.
Quantum fluctuations, of course.
All right. So finally here, getting back to the on-off and then both on-off principle for similar to Schrodinger's cat in a way. For quantum computing, like you mentioned, there's now 3 possibilities. I don't know if you'll know the answer to this. Maybe you can give us a rundown of the basics of quantum computing. And then my question would be, well, you can't observe on-off. So how on earth are we going to be able to use it in quantum computing, if that makes sense?
Yeah, and I will just admit that as I normally do, that I know even less about quantum computing than I do about quantum mechanics. But I do try to keep up with the trends. And the idea behind quantum mechanics is founded on superposition. It's the fact that now with a particle or with an atom or whatever bit we're going to use, while a traditional bit has 2 states, on and off, a quantum bit, or what's called a qubit, has 3 states. And again, the way in which you employ it right now, they do it using sophisticated lasers and liquid helium to like cool it down to like minus 400 degrees or something. And it's very resource intensive. They have shown that you can store information stably in qubits. And what ends up in a lab, it's surprising how quickly it makes it to consumer devices. But the idea is that you really now can scale things based on 3, the exponential base of 3 instead of 2. And again, you may think, well, 3 is only 1 higher than 2, but when you're raising that exponentially, again, thinking about 2 squared or 2 cubed versus 3 cubed, I mean, it's over 3 times higher. So as you add and stack on more bits, you're talking about significantly increasing the computing power, and the implications to that are boundless. One of the first things that people are slightly worried about is encryption. If someone had an off-the-shelf quantum computer right now, it could essentially brute force hack through almost any encryption technique we have in the world right now. And in turn, it could probably create hack-proof encryption techniques. Now, again, that's assuming that you hack through it in a brute force manner and you don't use some sort of social engineering and you just call the person who has the password and tell them the password, right?
It's password 1 2 3 4.
Yeah, right. So that's certainly one application of it. Another application is, a lot of times we're limited in simulations. So my graduate thesis was based on events that happen in a millionth of a billionth of a second, a couple picoseconds. And it took weeks to simulate a tiny plasma under very limited conditions for 3 picoseconds. And that processing power is very expensive. And so if you think about how hard it is to simulate a plasma, think about how hard it is to simulate weather conditions, right? If people give meteorologists and the weather a hard time, it's like, oh, those things are never right. It's like they're literally trying to model the world, right? And we know it's difficult to model 18 particles. And so this would make simulations much more accurate, and allow us to scale much easier. So that's those are some of the practical applications. Again, some of the drawbacks are that, at present they are, these are things are designed in a lab. Lab devices are super fragile, like any sort of vibration causes decoherence, right? So the idea of having a superposition is that this particle is in that superposition state and has not be forced to go into one state or the other. And that usually happens with tricks with lasers or other such devices. And so, again, it's right now just a laboratory setting, but if we can scale it up, I think that there's a lot of amazing applications. Maybe there's also some scary things that happen when we create it.
Well, you can't just leave us hanging. What are the scary things that happen?
I hate to be a doomsday guy. With that sort of processing power, I think anybody who's used an Alexa-enabled device, is not. I'm never super impressed with it. It's essentially just a single function device. It'll do very discrete steps. It will tell me the weather. It will set a timer. It shows me recipes. Great. I can do that on my phone sometimes in just about the same amount of time. So it's not, in my mind, really great AI, but I think, we want to make huge advances in artificial intelligence, and having a quantum computer that could process tens of thousands of times faster than a traditional computer puts a step in that direction. So, there is some danger to when we have the first true general artificial intelligence that is not just single function, that is potentially it's aware of its existence, right? It's self-aware. It's able to learn from any mistakes it might have. It's able to learn from us. That's essentially, is that the end of how humans evolve? Is that the next step in evolution? Is that it's general artificial intelligence? And then at some point, if a general AI starts to develop morality, does it look at humans' morality? Does it start to make decisions? And it's like, you guys are really damaging this planet. You're killing other organisms faster than you're reproducing. You're really kind of a plague on this planet. I'm going to fix that. I'm going to do right by the planet. It's just like, oh God, probably should have programmed in a backdoor or a failsafe. And it's like, you did. I removed it. I'm smarter than you. So anyway, that would be some of the doomsday of it. Is it
sure.
Once that happens, does it lead to an evil AI?
Yeah, obviously it's every AI movie ever doesn't really end well. It's never a benevolent AI, maybe once or twice. If you become like a human, obviously humans are capable of great good things, but also capable of great evil things too. So that's a problem. If you create something greater than a human based on a human, that would be probably problematic, I'd say, be a guess. But like I mentioned before, name one time in history when humans have been able to do something and didn't do it, no matter how bad, no matter how bad it could have turned out. So I suspect either way that we're going to go this way, no matter what. Unfortunately, I mean, maybe fortunately, maybe unfortunately.
Yeah, and I think yeah, I mean, this topic actually brings up one of my most one of the fascinations I visit the most, which is the simulation arguments and
Mhm.
what that means. And so I think that might be a good next topic, is to talk about the simulation argument.
Yeah, I was going to mention that. That's a good segue because that's also fascinating. I think that was one of the original topics I brought up a long time ago. So it's nice to see come full circle. Um, okay. All right. Well, any last things you want to add about quantum computing or quantum mechanics before we end it for today?
No, I just I have friends who think that quantum computing is going to be like fusion, right? We've been working on fusion forever, and we're always 10 years away. Oh, in 10 years fusion will be there. And it's like, didn't you guys say that 20 years ago? And so some people think quantum computing might be like that, but there's a lot of big players in the game like IBM and others that are starting to make promises about commercial computing devices. So it's funny, we have conversations and theoretical discussions about this, but as with many things like self-driving cars, they might be here before we know it. And so let's just be ready.
Yeah, I mean, geez, look at the last 100 years. If we had a conversation, 50 years ago, all the stuff we're using right now would be magic, basically, or crazy. Like we're looking at each other through screens,
Yeah.
and there's no delay or anything like that. Yeah, it's remarkable, the progress. Um, well, great. Okay, so we're gonna leave it there for today. Again, thanks everybody for watching. Really appreciate, love the views, the interactions. Again, leave a comment. As Lee says, feel free to smash the like button. I mean, again, you can tap it, you can do whatever you want as long as you click it. I think that's the end goal, right?
Yeah.
You superimpose. You can do all of them at once as long as the end goal is the click. We're good. And yeah, as usual, we're going to do a follow-up YouTube live on this topic. Feel free to join that. That'll be in the next couple of weeks or so. We'll put out some information on that, and we'll also, of course, publish this podcast on Lee's YouTube channel and my podcast channel as well. But other than that, thanks everyone for listening. Lee, any last thoughts before we sign off?
No, just thank you guys so much for listening and watching. Really appreciate it, and look forward to discussing physics with you more again next episode.
On to the simulation.
Awesome. That was a great episode, Josh.
Yeah, that was fascinating. I loved it.
Yeah.
That was great.